The myth of the magical messaging fabric. Let's just have a quick show of hands. Actually, no, we'll do this in reverse. Please stand up. Please stand up. Oh, come on. I've got the mic, I've got the power, everything, Okay, so sit down if you're not using messaging. Okay, everyone's using messaging. Fantastic. Sit down if you understand messaging. Perfectly. Perfectly. There's a lot of people who are kind of sitting up and standing out. You're not really sure. It's fine. It's fine. That's what I'm going to... You can sit down now. You can sit down. So this is what I'm going to talk to you about today. I'm going to really talk about messaging and some of the things that we think we know about it. Who am I? That is a very, very good question. My name is Jakub Korab. I'm an independent consultant specializing in messaging and integration. I've been doing this for about 10-ish years or so. And I've been doing this independently now for about 3 years. And what I've found going from company to company is that companies kind of tend to jump around between products if they don't work the first time. Does this sound in any way remotely familiar? Okay, good. So in doing so, they find themselves with a whole different set of problems to the ones that they had with the product that they've just jumped off from. Okay, so I'd like to help to shed some light on an area that a lot of people don't think about, and that's messaging. But before I do, I'd like to come to a definition about the title of this talk, and that is myths. What exactly is a myth? Well, some people say it's an idea or a story that is believed by many people, but that is not true. It's not bad, but I think it's a little bit simplistic. And it's quite dismissive of myths and the purpose that they actually serve. What I like to think of myths as is closer to this. It's a usually traditional story of semi-historical events that unfolds part of the worldview of a people, or explains a practice, belief, or natural phenomenon. So myths are stories about our world that are partially informed by our experience, partially through that of others, and how they help to guide us. And it's the usefulness of that guidance that is why we as humans have always told myths, because they have a grain of truth to them that helps fill in the gaps in our experience. The word mythology comes from two Greek words, mythos and logos. Logos, or logical thinking, approaches the world scientifically and empirically. It looks for explanations guided by things that can be proved through facts, experiments, and deductions. So truth that you discover through logos seeks to be objective and universal. Mythical thinking, on the other hand, mythos, approaches the world through less direct, more intuitive means. So truth discovered through mythos is more subjective. It's based on your individual feelings and experiences. So, with only a partial grasp on objective truth, like the blind men feeling an elephant, we fill in the gaps with mythos. So in IT, we're not immune to this. We're particularly susceptible to this, as a matter of fact. We have answers from Stack Overflow to the wrong questions. We have half-read tech articles, and we've got glossy presentations from vendors. So let's talk about how this applies to messaging. What is messaging? Well, messaging is fundamentally the movement of data between systems through the use of an intermediary. Messaging isn't glamorous. With any luck, it fades into the background. And yet it warrants more of our attention, since it's integral to so many things that we do. We all have limited time, and in an industry that's as fashion-driven as ours, where everything superficially seems to be moving so rapidly, people often focus on the shiny technologies, partially because they're cool, and partially because of a fear of being left behind. The ordinary things, on the other hand, don't necessarily get the attention that they deserve, and so we forget that they're there while we're busy doing other things. The people who looked in detail at these things, who knew the purpose behind them and the thinking, move on. And so we're left with gaps in our knowledge and half-remembered stories about what to expect from these systems. So we start to tell ourselves stories in the realm of messaging, such as, We will never lose messages. Messages will be processed in order. Adding consumers will make the system go faster. Messages will be delivered once and only once. And we should just be able to add this extra million messages a day and everything will be fine. And it all starts with one innocent statement. It's just a pipe. But if you look closely, you'll see that there's a lot more going on inside that pipe than originally meets the eye. So by telling ourselves stories, we assign something that is everyday and functional with wondrous powers. Later on, typically in production, we're disappointed with the results. To get past this state, we need to get a better understanding of what we're working with. Whether a messaging system can address your use cases and how it goes about doing it depends on its underlying design and the trade-offs that its authors chose to make. Sometimes they're obvious. Other times, you need to get a deeper understanding of what's going on, and this means drilling beyond the front page of the documentation and a few glossy presentations. So let's compare two products superficially in the same space, the distribution of messages. They have deep differences in approach and target use cases. My point during this presentation isn't to explain both of these in detail, although this will be a deeply technical presentation, but it's to highlight through their differences ideas that you need to think about so that you have the tools to be able to sensibly critique another messaging technology in the future. So let's talk about why we'd use a broker-based messaging system in the first place. Typically, when we have two systems, they agree on an interface. The implementation changes over time. This is standard practice. We're all very familiar with this. So why would we introduce a broker into the middle? Well, it's to further separate the two implementations, but this time not by interface, because that's a given. This is to separate them over time. Brokers act like a post office system. When you send a parcel, you don't need the recipient to be home in order for the parcel to arrive at their house, eventually. Yeah. We simply trust that once we've given the parcel to the post office, it will be delivered. So let's take a look at ActiveMQ. What are ActiveMQ's goals? Well, it's a free open source JMS implementation. It's a general purpose messaging broker with a wide set of use cases, which allows clients to interact with it through multiple protocols. A very broad overview of a broker kind of looks like this. You have your code sitting on top of an API, which is implementation specific. This is inside JMS. The broker infrastructure, which is normally called a provider in JMS terms, is actually spanning two different nodes. There's the broker that actually does the message distribution, and there's the client part that deals with the communication with the broker. In between, there's a wire format. You can't definitively say whether a messaging configuration is right by looking at one side only. You can show me a broker config and go, does this look okay to you? And I'll say, does it start? I don't know, what are you trying to do with it? You have to take the entire thing into consideration. Beneath this API, you don't really care what happens. Messaging is a lot like a sausage. You don't really care what's inside as long as it tastes good. So the client-broker communications are through this wire format. So what exactly is this? Well, these are client-agnostic ways to actually interoperate between a client and a broker. You've got OpenWire, which is an internal one within ActiveMQ. You've got AMQP, which is a standardized wire format, which is gaining traction in the industry even further. Stomp, a text-based one. MQTT, for people building out IoT-based systems. There's XMPP, which is kind of interesting if you ever want to talk to your broker like it's a chat room. And it does WebSockets, which is pretty cool. So ActiveMQ actually supports two different types of what are called messaging domains. The first one is point-to-point, implemented through something called queues. Queues are a first in, first out data structure that is durable. What exactly is durability? Well, durability, no consumer, no problem. If I'm a consumer, I connect, I get some messages. If I then disconnect and more messages arrive and I connect, I'll get the messages that arrived while I was gone. It's equality of service. Messages are additionally persisted if the client, if the sender wishes them to be. So they survive a broker failure. Durability doesn't equal persistence, although they're very closely related. This is the domain that we're going to focus on simply because this is the one that people are most often interested in. About 90% of messaging has to do with queues. The second one is publish subscribe, which is topics. Topics are non-durable, so they're a bit like a conference call. You dial into a conference call, you're listening to whatever is going on in the conversation. If you drop off for a second because someone interrupts you, you come back, you've missed the conversation that's been going on in the meantime. So client subscribers or consumers can be made, so these things can be made durable so that the subscribers actually do receive what's been happening in the meantime when they were disconnected. Durable subscriptions can also take advantage of persistence, which is quite a nice feature. Now that we've got some basic definitions, let's discuss a trade-off that all single node systems that write to disk and interchange with data have to deal with. Now this doesn't just apply to message brokers, this also applies to databases. On one hand you've got reliability, on the other hand you've got performance. You can put an arrow anywhere. This is the JMS default. You can, of course, move that arrow anywhere along the spectrum through different types of configurations, so it's tunable. To understand how this might be tunable, how it might be achievable, let's take a look at how brokers actually go about storing messages. Well, they do this through something called a journal. What's a journal? A journal is a persistent data structure. It contains a history of interactions spanning multiple files. In the case of ActiveMQ, it stores messages that have come in and also acknowledgements from clients when they've actually gone through it, when they've processed these messages. So let's take a look at a very simplified model of how messages actually end up in this journal. How would you go about sending a message? This is necessarily simplified, but it's a decent working model. A producer comes along, there's an application thread, and at some point in time it says, I'd like to send, please. So the JMS client will actually go off and talk to ActiveMQ and say, okay, here's a message. ActiveMQ writes the message and gets a confirmation. What's this confirmation? Well, a confirmation is just a bit of safety. Did this actually make it to disk? What do you mean? Once you've made it to disk? You've just written it to disk. Right? Well, a second. Once we've gotten into this confirmation, we'll do the acknowledgement. It's this confirmation that is actually the longest step during the sending of a message into a broker. If I let's go back to writing to a disk. If I've written to a disk, why would I need confirmation that it's actually been written to a disk? Operating systems are a lot more complicated than we think. The tech stacks that we work on are a lot more complicated than we think. When we write to a disk, you first hit an operating system buffer cache. This cache is frequently read blocks and it combines disk writes together. You then have a disk drive controller cache. Some of these are write through, some of them are write back, so they buffer up a bunch of stuff and then write it out. Usually they're volatile. If you turn off a computer, anything that's in the RAID array that hasn't made it to disk, gone. Then once we've gone past this drive controller, we end up at the actual disk drive itself, which also has a cache, which is also write back, usually, in consumer drives, and it's volatile. Turn the power off, it's all gone. So, in order to actually make sure that we have gotten something to a magnetic spinning platter, or a piece of RAM, as the case may be, we want to actually flush through all of these buffers and make sure that it actually goes to the bottom. And that's the really, really time-consuming thing. So only the operating system actually has control over communications with the disk drive controller. So the only thing we've got available from a Java process is this: sync. Force all the system buffers to synchronize with the underlying device. Cool. In ActiveMQ, disk is the main speed limiter. Yeah. Performance-wise, it laughs at most things that you throw at it, as long as you don't decide to put it to disk. Then you got some problems. So what are some of the performance factors around a disk? Well, again, let's use a simplified model. So here we're going to use the analogy of a pipe. We have width. The width of a pipe is the actual carrying capacity. Yeah? How big can the things that I'm writing down actually be? In a single step, in a single operation, how big is this entire thing? Yeah? We have the length of the pipe, which is the latency. How long does it actually take to traverse that entire pipe? Yeah. And then how many things can I actually put in the pipe within a period of time? This is a measure called IOPS. IOPS are a bit of a weasel word used by drive manufacturers. I/O operations per second, because they mean different things. Okay? You can get different IOPS measurements on the same disk depending on whether you're doing writes or reads or a combination, and whether they're random or whether they're sequential. Because you remember, you're generally moving heads, spinning platters, etc. So the overall performance of a disk is going to be the first of these limits that ends up being hit. Okay. Beyond this, we've actually got internal contention. Because if we're writing to a single file, we can't have multiple threads writing to a file at the same time, because that would just corrupt the entire thing. So we need to deal with contention inside the broker's storage engine in here. So we've got a mutual exclusion mechanism here, so that if I've got 3 producers that all send messages at the same time, they line up behind each other in order to write to the disk. And this is what slows things down quite a lot, because effectively, writing to a single file is single-threaded. So the upside of this design choice to put all the messages in the same journal is that it's very easy to implement transactions. Using transactions means that the broker can make certain optimizations around the communication, the provider, I should say. So if you think about what a transaction actually is, a transaction says, do all or nothing. So I don't need a confirmation every single time I send a message. I just care about it at the end. So the client will actually send a number of messages across asynchronously, not caring what's going on. It just basically just throws it at the broker. And then the final step goes commit. Commit, write, confirm, ACK. This gives you orders of magnitude higher performance gains. Being a transactional resource, brokers can also tie into broader transaction management APIs like JTA so that you can tie other things into the same transaction if you so wish. So let's now take a look at consumption. So if I want to consume a bunch of messages, how exactly does this work? Well, I've got a journal, I've got a store, I'm going to page a bunch of messages into memory, and I'm going to dispatch them over to a client. That gets dispatched into something called a prefetch buffer. Yeah? The client actually consumes out of this buffer, and at some point in time acknowledges. There's a reason this is a step X and not a step 3. I'll get onto that in a second. Once ActiveMQ has received an acknowledgement, it deletes. Okay? It doesn't really delete. It simply stores an acknowledgement in the journal and increments a pointer. Okay? So the acknowledgements are stored in the journal so that even if all of the indexes, etc., are corrupted, a broker can get back to its own current state simply by reading through all the journals and replaying all the stuff that's gone through beforehand. Journals that have had all of their messages deleted, individual journal files, will be deleted through a background process. Okay. So what exactly happens on a queue if I've got multiple consumers? Well, if I'm getting a stream of messages coming through, I get a round-robin dispatch between the current consumers that are around. What happens during the actual during failure? Well, during failure, the broker will actually take the messages that have been dispatched to this client that it never received acknowledgements for and dispatch to them to C2. This is a really interesting point here to understand. Because what we've been doing is we've been taking a message out of a buffer, processing it and acknowledging it. 3 steps. Think about the timing of a potential failure of this node going down. A broker has no insight into how far through those 3 steps you've actually gone. You may have actually talked to a back-end system and triggered some sort of state change at the same time as you crash. The message, however, because it was never acknowledged, will be resent to another consumer, and the second consumer will do the operation again. So you may get the message being processed twice. Now, the impact of this is that the best that we can hope for here is at least once delivery, which means there is actually no such thing as once and only once. This has fundamental implications about how you need to think about your message processing logic. Because you should assume you will get duplicates. Let's talk about broker reliability. The broker here connects to a store, which also provides a locking mechanism. This is a master-slave model. It's traditional in IT. You see it around databases all the time. The store here provides a locking mechanism as well. So that who is the master, who is the slave is completely non-deterministic. 2 physical nodes act as a single logical node. Master election is based on who turns up first. Okay? That broker gets exclusive access to the lock and is able to open its port. So the client, in the meantime, has got this failover string, and it's saying, connect to one, connect to the other, connect to one, connect to the other. Okay, I can't connect to either of those. I'll just keep retrying. And eventually it connects to something. Okay? Which in this case is box A. If box A goes down, the port disappears. Box B gets the lock on the store and is able to take over where box A left off. The client, on the other hand, because when it detects a disconnection, it just goes 1, 2, 1, 2, between one and the other, and until it eventually finds a box that's got a port open. Okay? So in this particular setup, how our disks are actually put together matters. Aside from setting up shared disks, we need to ensure exclusive access to prevent side processes coming in and using this disk, because otherwise you get mysterious slowdowns in your brokers. Someone decides to run a database report on something that uses the same disk. Yeah. All of a sudden, your throughput just goes. So this is a big problem in virtualized environments particularly that don't have something called storage affinity, which is exclusive access of a particular virtual slice onto a disk. Okay? We need to guarantee a clear run to the disk with that minimal amount of contention. So brokers like ActiveMQ aren't a particularly good fit for containers. Not just ActiveMQ, Kafka doesn't really fit very well into containers either. We'll get onto that later. Basically, you need a manual box setup. You care about where your disks are. So this idea of moving things around and just getting anything to talk to, anything can kind of pop up, anywhere, doesn't really work here. There is work actually going on here further. So how do you scale this up and out? Well, you can increase the disk speed. How do you do that? Well, you can get a faster disk. That's always a good thing. You can make better use of the 3 different disk dimensions that I've spoken about. Maybe use some transactions. Okay? So here what we're doing is we're increasing the size of the thing that we're sticking down the pipe rather than worrying about the number of things going down the pipe within a second. We can also split messaging over multiple brokers. This is a really, really crucial idea. Because what I see on site a lot of the time is this. The big bag of messaging. Hey, I've got all these systems that need to exchange messages with each other, asynchronously. So we're just going to ActiveMQ is kind of a thing that exchanges messages asynchronously, isn't it? So let's put that in the middle, and everything will be fine. And it's based on this one idea that anything can talk to anything. Don't do this. Please, please, please don't do this. If you replace the ActiveMQ block here with Oracle, I've got a bunch of things that need to talk to Oracle. Is it the same Oracle? Don't know. Probably not. Yeah? So a little bit of thought is required. Yeah? So this is what I call a conceptual diagram. You need to actually break this design down further. So what are some trade-offs about ActiveMQ? Well, it's a simple model. In my mind, it's actually a little bit too simple. You download it, you install it, you go, and everything works for about 6 months. And then it stops, and no one's got any idea why. Yeah. It's transactional, and it has a rich set of supporting functionality. So you've got message routing, filtering, wiretapping, broken networks, all sorts of interesting things. Some negative things, because everything's a trade-off. Well, your performance is pinned by the disks. Yeah. It's also impacted by the total load on the broker. Yeah. We've already seen there's contention going on. And it requires non-transparent changes to broker topology over time. Which systems use which brokers? So the triggers for some of this change might include traffic volumes, number of destinations, the payload sizes that end up going through the system. They might be bigger than what we expected. We might have more systems that need to talk to each other. And fundamentally, it requires an understanding of the internal mechanics and some upfront thought to get right. You're not going to get out of this. You need to understand what's going on. So as a counterpoint, now that we've discussed a classic broker, let's take a look at Apache Kafka. Apache Kafka was designed at LinkedIn to get around the problem of multiple separate data feeds from different systems that use different transports. And they said, well, hang on, wouldn't it be awesome if we could just connect everything to everything? The big bag of messaging. It's intended to address some of the perceived shortcomings of ActiveMQ. Namely, the need to not set up separate brokers for different purposes. The things that it's actually used for is moving logs, notification of UI activities, monitoring events. So what are its goals? First one is be fast. How fast is it? Oh my Lord, is it fast? It's beautiful. It goes faster than a disk can write. Amazing. It handles huge, huge, huge volumes of traffic. Yeah? How huge? Well, if you're looking at hundreds of thousands or millions of things per second, Kafka's probably the tool for you. It scales horizontally. It supports pub/sub and point-to-point. And it allows the no-cost addition of consumers. So adding consumers doesn't slow the system down. It also permits replays of messages. ActiveMQ doesn't. You consume a message from a queue, the queue, it's gone, right? That's the way a queue works. Not so much in Kafka. It achieves this through a unified destination model called a topic, which I've disambiguated by calling it a Kafka topic. So unlike ActiveMQ, Kafka uses as one thing for both topics and queues, pub/sub and point-to-point. It does this through having one journal with multiple pointers to internal locations within that particular thing. Well, what's this pointer? Well, pointer is a shorthand name that I use to conceptually get across what this actually is. It is a log offset. It is a pointer to a location in a journal file. Okay? It is controlled by something called a consumer group, which in code is referred to by group ID. A consumer group designates a single logical consumer. By logical consumer, I mean a system. So how exactly does a topic work? Okay, so here we've got a topic. It's a journal. You write some messages into it. A client connects, has a pointer at the beginning of the file, moves across, messages get sent. One pointer. Another consumer comes along, it gets another pointer, which moves along and messages get sent to it as well. Having n pointers means that a Kafka topic acts as a queue where only one pointer exists and a topic where many pointers exist. Okay? So if we've got one pointer and one consumer, this all works really, really simply. Now what about if we actually have two consumers and one pointer? Remember, one pointer corresponds to one logical system. Okay? So if I've got two threads in that system that want to consume out of that one journal, what's going to happen? Well, ActiveMQ did round-robin dispatch, if you remember. With Kafka, not so much. The second consumer comes along, and it steals possession of that particular pointer. So a new consumer takes over the consumption of the message flows. It's kind of like a consumer priority feature, which is a type of exclusivity, where in this case, the newest consumer has the highest priority. Okay? This is confusing for newcomers because you're kind of used to it. Well, it's a queue, right? I've got two things on a queue. They should be getting half the messages each. What's going on? So this is completely different from the way that JMS operates. So the Kafka docs actually suggest that if you want to process messages in parallel, you might want to multiplex. So you have one consumer which puts onto some sort of internal memory structure, which then hands off to a number of different threads that actually do the processing. Well, the problem with that is that if you consume a bunch of messages, the crash of a consumer will drop any messages that are currently in flight. And there's no way to keep track of this. So there's another way to get multiple consumer threads for the same logical system, and that is partitioning. Partitioning is native to Kafka in that messages for a single topic get actually split out over multiple journals. I said that it was one journal. Kind of, not really. You can have it on multiple journals. So the journals themselves are referred to as partitions. You can also think of them as shards. Okay? So what happens? Well, if I've got two consumers for the same pointer, they both correspond to the same system. Consumer 1 comes along, it gets some messages. Consumer 2 comes along and it gets a bunch of different messages. So what about if you've got less consumers than you've got partitions? Well, that's pretty straightforward. It controls both pointers. Gets assigned multiple partitions to the same consumer. So how exactly does partitioning happen? Well, unlike ActiveMQ, where if you want partitioning, you have to build some sort of an application level thing before actually performing send. So you're sending to multiple locations in effect. In Kafka, it's built in, sort of. So partitioning itself is actually performed by the producer. To understand how this might work, we have to first understand what exactly a message is. In ActiveMQ, in JMS, it's an object. There's some metadata, some headers, some properties, and a payload. In Kafka, a message is a key-value pair. Okay? Partitioning is performed through a function. Well, they're given a message, and the current cluster state around this particular topic that I'm about to send to, which partition should I send to? Okay. So what exactly is the, we can probably guess that the value is probably the payload. So what exactly is the key? Well, the key is a business-specific grouping for partitioning. It corresponds to a set of messages that should be processed in order. So it might correspond to an account number or a geographical location, for example. Okay. The partition function is actually provided through the implementation of an interface called a partitioner. The default implementation uses a hash function, which leads to an uneven distribution due to hash collisions. Okay. This is especially true of a small number of partitions. If I'm hashing into two buckets, chances are one of those buckets is going to get far more messages than the other. Okay? So there's another issue here. If we want certain messages to be processed in order relative to each other, we might run into problems when we're adding partitions at runtime. Because a later message might be put into the newer partition and the pointer from that partition gets processed first. Okay? So some partitioning considerations that you need to think about. Well, you need to ensure that all related messages end up on the same partition, first and foremost. You probably want some sort of an evenness of distribution. Hashing is okay, up to a point, maybe. You get uneven load on the various disks going on inside your infrastructure. You probably want a stickiness of a key to a partition when the cluster topology changes. So if I'm sending stuff about a particular account to one partition, and I get a new partition added into the cluster for this particular topic, even if a new evaluation of that key would point it to a different partition, I still want it to go to the old one. That's something that you might want to do. Now the problem with that is, if you've got that sort of like logical state in your partitioning logic, well then you need to share that state across producers so they're all producing in exactly the same way. And that needs to be coordinated through the cluster of producers that are currently sending into the system. At this point in time, you're kind of thinking, wow, holy cow, this is quite involved. Why? Why? What am I actually getting out of this? Well, you're doing this to support a fair distribution of messages to multiple consumers without incurring the cost of managing dispatch. So a lot of the slowness in a regular broker has to do with the paging of messages and distributing them around to a number of clients. So the more consumers you actually have in a regular broker, the longer it'll take to distribute messages amongst them. With Kafka, you can just keep adding consumers and the system will scale linearly. But in order to do that, Kafka rephrases the distribution dispatch problem to one of partitioning. So it moves the responsibility for fair distribution of messaging to you. Ta-da! Well, at least that's that, right? Okay. No, you're not getting off that easy. So when we actually send a message, we've got this interface to a producer. Send a record, which is the wrapper around a key value pair, but it gives you a future. Oh, whenever you see a future, you should just go, oh, this is terrible. Because the future is not now. So what it actually sends to is the client library, which has a little queue inside it. So you got a number of messages that you're just sending into this thing, and you're thinking to yourself, wow, this is amazing. Kafka's so fast. It's sending faster than you can write stuff to a disk. Well, guess what? Whenever you see that, it's not writing to a disk. And so if you've got a number of messages in this buffer and the client goes down, the sending system goes down, what happens? Can you replay? Well, at least it's fast. Well, you can tune it to be more reliable. There's a number of different things that you can say. You can set the buffer size to 0. You can make the call synchronous. And you can wait on the future. Thankfully. That's all we have to worry about then, right? Not quite. The leading question. Because the way that we consume messages off the system is through a single poll operation, which has one little thing that's highlighted in red, records. So it gives you multiple things at the same time. Be careful. What happens when we poll? Well, the pointer movement is actually unrelated to whether or not the messages get processed. Yeah? A crash of the consumer means that you have no idea what just happened with those messages. The pointer has already moved. The offset's been incremented. So when another consumer takes over, it actually has no idea that the failure happened in the first place, which means that consumption is non-transactional. So what do you need to do? Okay, well, here's one scheme. You can keep track of the last consumed pointer position, the offset, manually. And whenever your consumer is assigned to a partition, look up the current state of where you think you're at and rewind to the last known offset. So you'll just consume from the last thing that you thought that your system was up to. Yeah? There's a seek operation to do this. Alternatively, you can keep track of the messages that have been processed. On partition assignment, you rewind all the way back to the beginning and you discard previously seen messages. Idempotent consumer pattern. Or you can keep the consumer code simple and only use Kafka when some message loss is acceptable. This is the A10 Thunderbolt, also known as the Warthog. It is the most survivable plane ever built. It is used for close air support and military operations. It attacks tanks, vehicles, and ground targets. It is designed to fly with one engine, half of a tail, one elevator, and half of a wing missing. And it can survive direct 23mm anti-aircraft fire. Kafka's like the Warthog. ActiveMQ had a traditional master-slave design. It's old school, a bit like a relational database. Kafka, on the other hand, has been designed cloud-first to run on simple commodity hardware. It is the NoSQL of messaging. Each Kafka topic has a leader. Each topic partition has a leader. And followers, master and slaves. Yeah? Doing replication between them. Kafka keeps track of in-sync replicas. So it consumes from any partition which is deemed to be up to the latest position. Yeah? So through that, all you need is one thing remaining in that entire cluster, and it'll just keep consuming. Yeah? This is magic. So all of the reads and the writes end up going through the leader. The followers are just keeping up. The client sets up how many commit responses they want when they send, and how many responses they want from the replicas before continuing. So with Kafka, it's actually a really interesting scenario, because where we had a master and a slave, we basically had one box that was sitting around doing nothing. With Kafka, all the nodes can be doing something. So given a 4-node cluster of Kafkas, some can be masters or leaders, and some can be slaves for one topic, and the same box can be the leader or the master for another topic. The actual coordination of this is done through Apache Zookeeper. This keeps track of the nodes that are present in the broker, the topics in the partitions that have been maintained, who's the leader, who's the follower, consumers, consumer groups, and where the journal offsets are pointing to. So the implication of this, well, you have no need for shared hardware. Awesome. There's no need to sync. Yeah. You just spray the same message out to a whole bunch of nodes in the cluster, and most of them, and eventually you're okay with that. You get reliability through redundancy, so you don't need to be guaranteed that every single node has written down. Yeah? So what's the implication of this particular choice? Well, up to 3 orders of magnitude higher performance than a regular broker. So they're positive trade-offs. Everything's a trade-off. It's easily scalable. There's a high throughput due to the resiliency design. And it's super easy to run on commodity infrastructure. What are some negatives? Well, it's non-transactional. There's lots of client complexity that needs to be re-implemented across systems and languages. So you may decide, okay, I've got this strategy for dealing with these issues. This is in the Java side of the things that I am building. But I've also got this Python stuff over here. I kind of need to do the same over there. No? It needs lots of disk. Messages aren't deleted when they're consumed. You can rewind a cursor. There's a background process which deletes journals or compacts them. By default, this happens once every 24 hours. So to avoid message loss during prolonged consumer outages, you actually need big cleanup windows to make sure that files don't get cleaned up before you've had a chance to consume them. Because the background process doesn't care where you're up to. It can delete files that have messages there. So these big cleanup windows can get very expensive disk-wise. 20,000 messages a second at 1 kilobyte a message is 72 gigabytes of disk space per hour. That's quite a lot of disk. And disk might be cheap, but it's not that cheap. Finally, it requires an understanding of the internal mechanics and some upfront thought to get right. And for the eagle-eyed, you'll notice that this point is kind of common to both of them. You kind of need to know what you're trying to do with it. So what works for you? Well, you'd use ActiveMQ when you've got high individual value messages. Okay? You care about not missing messages, and you want them processed in order. Kafka doesn't actually lose messages, you just might not consume them. The use cases in ActiveMQ are actually very broad. So you can use it for things like non-durable pub/sub topics, right? You don't need to actually go to any disk at all. Like, why do you need to, if you're sending out prices for something, or you're sending out temperature measurements, or some sort of telemetry, why do I need to persist that at all? You might be using the broker as a transport bridge. So I've got a JavaScript WebSocket client and it's talking to a backend system that's using C++ and AMQP 1.0. You might be doing request reply over messaging, a contentious area. Actually, when you consider all of the failure cases that it actually has, there are no less than 5 failure modes for request reply over messaging between a consumer and a producer. Yeah? Be aware. You get simple message routing in the product, and it easily spans multiple geographical locations on a selective basis. You say this topic gets broadcast there, these queues get moved over here, queue messages get moved over there. So when would you use Kafka? Sorry, I apologize to the guy who was taking the photo. Quick. Da-da, da-da-da, da-da-da. In the meantime, jazz hands. Ready to go? Ready to go? All right, awesome. So when would you use Kafka? Fundamentally, you would use it for messaging that is valuable in aggregate. User activities, log aggregation, UI performance, disk events, clicks. Yeah? So if anyone works in affiliate marketing, this is your baby. Yeah? You do it when you have a huge throughput of data. ActiveMQ is limited by the syncing. Yeah? There's a general... these two things are actually related. The less data you have, the more valuable it is. Likewise, the more data you have, the less valuable any individual piece of it is. Just a thought. You might be doing stream processing. Anyone heard of stream processing? Anyone heard of staged event-driven architectures? Do some processing, put it onto a queue, do some processing off that queue, put the result onto another queue. That's stream processing. I've just saved you a whole bunch of conference presentations. You can buy me a beer later. Or you've got it for event sourcing. What's event sourcing? Well, in event-sourced applications, any changes to application state are stored as events. And you can rebuild the total state of a node by replaying all of the events. So Kafka and event sourcing are kind of like, I'd say peanut butter and chocolate, but that's not a very British thing. It's like tea and milk, if you're from up north, I suppose. They go well together. In short, horses don't fly. Neither platform gives you everything. Transactions, consumer failure awareness, effortless scalability, storage transparency, and drop and go in production. Some of these you get, some of those you don't. Some of these things are good, some of these things are not so good. It all depends on your use case. Yeah. So having said that, use the right tool for the job. There's nothing that says you can't use both, but your architecture will likely skew one way or the other. Yeah. NoSQL didn't replace relational databases, it simply filled niches. In the same way, Kafka offers an alternative complementary toolset to traditional messaging for different types of tasks. So understand your tools, use the right tool when it makes sense. And remember, more logos, less mythos. Thank you very much. You've been a great audience.